Welcome to the last chapter of this lecture, Mobile Communications, Chapter 7, the Outlook. So, what can we say about the future of mobile and wireless networks? Is it the 5th or 6th or whatever generation? So, yes, it will be fully IP in the core. Is it a license, a public, a private network? Do we have many micro operators or only just some few big operators? Will we really have trillions of devices, terabits of a second connection, sub-microsecond latency? Will we have artificial intelligence in the network? What about a wireless tactile internet? That means as soon as you touch a surface, the surface will respond. Everything is connected with the help of wireless technology. Let's go back. You remember this idea of we want to be always best connected, whatever it means. So maybe at home with some 100 megabits per second a gig, and if you are traveling several hundred kilobits per second, well, sometimes megabit per second, whatever. So that was the idea, and this is still the idea. But maybe in the future we'll have higher data rates, better service, lower delays. What else did we see in history? We saw the fusion of many different technology. We covered here a lot about cellular phones. There were analog phones in all the different digital generations. We see satellite communications, cordless phones, wireless LANs, and well, we see that basically everything comes somehow together in this kind of 4th generation, fully internet-based networks. We saw that LTE can make use of wireless LANs. Wireless LANs take over some of the LTE technologies. We can integrate satellite technologies, etc. Okay, but what is maybe new? We saw also, besides this wireless technology, a convergence of many other networks. So also the fixed networks, they use everything over IP, common technology. Different company networks with former proprietary systems now use the classical IP technology. Mobile networks, as we saw, the classical internet now offers services like voice over IP, cable networks, internet, television, IPTV, all different kind of home networks, social networks, whatever. We do a lot of content sharing. Everything uses this common technology. What else do we see? This is kind of history. Now we see also many new things coming in using the same common technology. Internet of Things, many different industrial control systems, but also the electricity, the power grid, different medical devices attached to some other devices using internet technology, also with wireless access, autonomous vehicles, etc., etc. So that's new. And we see this transition going on right now. What else do we want to have? Well, I told you in the very beginning something about the global goal of this kind of overlay networks that gives you this always best connected. Is it on the campus, or if you move through a city, regional networks, back to your home? There should be a seamless roaming, not only within the same technology, but also, and that's what's our vertical handover, between different technologies covering different regions. And we had this example of, well, we can now go from LTE to Wi-Fi and back, etc. So there is some vertical handover. There's still some way to go, but now we see this integration of different types of fixed mobile networks with really completely different transmission characteristics. What else did we cover in the lecture? We saw many different networks with different characteristics, like a classical Bluetooth with something like 1 or 2 megabit per second for slow mobility, 3rd generation technology, 4th generation technology, already covering high data rates at relatively high speed. Different types of wireless LANs, they're not really made for high speeds, but pretty high data rates. And there's always this physical but also economic border. So, because either it's not feasible with a certain technology to do something like higher relative speed, like more efficiency, lower delay, higher data rates, whatever, or it's simply too expensive. And then somewhere is this promising 5G. So 5G together with new radios should shift this border a bit. So higher data rates at higher speeds, lower latency, etc., etc. Why do we want to have this 5G technology? I will come back to what it is in a second. Because we can think of many interesting new applications. For example, I already mentioned tactile internet. Okay, that was in the upper right hand corner. That requires high data rates and really, really low delay. Okay, maybe we need some edge computing for this, etc. But then there's also something like a disaster alerting system with, well, reasonable delay, very low data rates, but this has to be ultra reliable. The same is for the emergency calls in cars, the e-call systems. Then we maybe have something like real-time gaming. Okay, 10 milliseconds delay, well, we can tolerate this, and 10, 20 megabit per second, that's okay, unless we want to have augmented and virtual reality systems. We will have our personal clouds, we have our multi-person video calls, but if you look, if you want to go for autonomous driving, delays 1 millisecond. Augmented reality, virtual reality, these things, they might require a bit more. We can discuss this. So, the legacy networks here, they cannot really fulfill this. We need new networks. And that was one of the ideas of, okay, we should go one step further than the LTE, LTE Advanced Pro. We have to come down with the delay, we need higher data rates, we need more reliability. At the same time, also in the fixed network, something happened. And this has to do with so-called software-defined networking. What is the idea of software-defined networking before we go to the mobile networks? The idea there is, SDNs as they are called, we want to have a very dynamic and efficient network configuration. We don't want to buy new hardware for different jobs, but we want to reconfigure in a very convenient, simple way our network. Well, to have improved performance. So we see, maybe you remember, in the classical internet, everything, the data and the control, that's all mixed somehow, but with the SDN we see again a separation of data forwarding and a kind of a control plane, brain. So that's the brain controlling the network, and then extreme efficient systems for forwarding data. If you remember, we had something in the classical intelligent networks. It was by far not as flexible as software-defined networking, but the idea of the separation of control planes and data planes, we know this from our cellular networks, classical telco networks, and we also have something like this here in software-defined networking. So, why do we want to have this here in our mobile scenarios? Let's have a look at this, well, maybe confusing picture. What does it tell us? So, we have several network operators. Okay, it doesn't exist anymore. It's O2. Several network operators operating the network. The goals of the network operator, well, quite clearly they want to make money, so they want to use their hardware as efficient as possible. Already today they share parts of the hardware, they have their own networks, but it's a huge investment. What else do we have? We have a lot of content providers like the Skypes and the Amazons, whatever. Disney, also a lot of social networks, and they have certain requirements. So they, for example, want to offer their customer a very nice experience watching the newest video in 8K over their mobile device. They do not operate the network, but they have these types of requirements. So they need certain quality of service. And then we have many different, applications, so updating mechanisms, quality of service, insurance. We have algorithms for orchestration of different services. We need security services. We need accounting, billing, etc. And you can imagine that there are certain costs for the network operators, and there are certain costs for certain content. In the end, the operators want to get money, the content providers want to get their money, etc. And maybe there's someone operating the network itself, so base station operators, whatever. So there are many different models possible. Okay, how to control all of this? How to do kind of efficient scheduling of different services? How to schedule the resources you have? In the end, you have to program all the components in the network, the routers, the base stations. In the end, you need certain resources in your antennas. So many different components to orchestrate. Not that simple. What is the second component and how does it all come together? So software-defined networking is known also in fixed networks. But this can be complemented by so-called network function virtualization, NFV. What does it mean? We can now virtualize network functions. So we do not have to buy a certain piece of hardware for a certain function, but we have software implementations of certain network functions. And to create a service for, some user or for a company that wants to offer something, we can chain different functions. We can use functions for many purposes, like quality of service, like certain reliability, certain security, etc. And now this is for you to look up. The idea is that the software-defined networking approach could basically orchestrate and manage these many different virtualized functions. So this is how it comes together. So this is rather a pointer for you to look into these aspects of software-defined networking and network function virtualization. Okay, so we have the new requirements, demands for new services. We have many content providers, network operators, many different companies in between. We have to manage all this to achieve what? Well, that's what IMT 2020 is. 5G, applications for 5G. This is what we, in the end, want to offer, for example. So maybe there's someone that wants to offer gigabits per second. Great. Someone else wants to have a self-driving car. Okay. Yet another one wants to offer a smart city service covering millions of devices. And then there's all this 3D video, augmented reality, automation, smart building stuff. It all in 5G boils down to three large application fields. One is called eMBB, Enhanced Mobile Broadband. So this is where we have our gigabytes per second. Enhanced because it's more than LTE can offer right now. Then, if you want to have millions of devices or billions, we have the so-called massive machine type communication. So it's machine to machine communication. So it's a special type of communication. This is not voice, this is not video, audio, but these are some bytes here and some bytes there. It's called MMTC. And the third area, that's the ultra reliable and low latency communication, URLL. That's what we need for our self-driving car, for many critical infrastructure, ultra reliable. It has to work 99.9999% of the time. And ultra low latency. So 1 millisecond. That would be great. So these are application domains for 5G. And you see, with LTE, okay, we can do voice, we can go a bit in this direction, we can go a bit in that direction, and just a little bit in that direction of this ultra low latency. So, if we compare IMT Advanced, this is our LTE Advanced Pro, what we have today, typically, you see, okay, latency 10 milliseconds, but we want to have 1 milliseconds. Mobility 250 kilometers an hour. We want to go up to 500 for the trains, for example. Also the data rates, peak data rates, well, 1 gig, we want to have 20. Things like this, but also efficiency in terms of energy, spectrum, that's important. How many devices can we support? What is the traffic per square meter, or better per cubic meter? The connection density of devices. So, you see, many different aspects where we want to go beyond IMT Advanced. But it's also quite clear, at least right now, there's not an application that requires everything. And we will not see pretty soon devices that can fulfill everything, all the requirements. So if you map this on the main usage scenarios, you see, okay, we have this massive machine type communications. That's important, connection density, because in a building we have tens of thousands of devices. Or for our autonomous cars, we need mobility, high mobility, low latency. Autonomous, aircraft, these UAVs, for example. So, ultra reliable, low latency. Not extremely high data rates, not that high connection density. And then we will have something like this, our mobile broadband, where we really need high traffic capacity for a certain area. User experience data rate has to be high. Well, latency, okay, and connection density is not that high. So you see, this is when we map the usage scenarios to, well, what we all want to have from 5G. So, what happens to our LTE? I told you, the very beginning of LTE does not suddenly stop, and now we have a new technology. So LTE, this is this long-term evolution. And we see that after release 14, release 15 will follow, then 16 and 17 and 18, etc. So it will continue. And basically, starting with release 15, we can say here we have the initial 5G standards. So that means we have new radio access technologies, for example. We look at higher frequencies. We look at new feature, other enhancements. So we have new requirements. So it's a kind of an evolving process of proposing something, specifying something. And you see that here in the release 15, we see at least, okay, how can we support this massive broadband and IoT? How can we extend this then to a new spectrum? How can we then meet all the requirements? So this takes some time. So release 15 does not meet all the requirements of IMT 2020. So this takes some more time. But this is what we used from LTE. This is what we saw at 3G, etc. So to summarize some new features, we'll see 5G goes to higher frequencies, up to 52.6 gigahertz, uses way more bandwidth compared to today's system. That's similar to what we do at wireless LANs. It's also more efficient. So more bits per second per hertz, downlink, uplink. You saw the different use cases. Some need some kilobit per second, but ultra reliable. Some others need gigabits per second, but okay, reliability, who cares? Then we have some dropouts in the video, so okay. Some more technical thing, time slots and resource units in LTE, when we have frequency, part of the spectrum, part of time. Now we have even mini slots needed for ultra low latency responses for the autonomous cars, factory automation. So we even further subdivide our time slots. For example, in the 3 areas, or eMBBs, we want to have this high mobility, high peak rates, and all the data should be available all the time. The ultra reliable low latency, sub-millisecond air interface latency. Okay, that's not that simple. 5 millisecond end-to-end latency. Okay, definitely this is not around the globe because we have speed of light as the limit, but then we have to think of edge computing for computing these things. Reliability, 4 nines. But, well, decent data rates. Machine-type communications, billions of things connected. Very cheap, very low energy. But you see how many devices per square kilometer. Yeah, think of a city. Think of a factory, industrial plant. Plus, we have requirements like 10 years battery life. That's also not that easy. And you will also see we have a new core, the so-called next generation core, that uses SDN and NFV. I told you a bit about this. But it's also a self-organizing network, SON. Everything is now virtual. Quite similar to what we have in our normal computers. We have cloud computing, virtualization of CPUs, of memory, of everything. Because this is way more flexible. That's the idea. How does the architecture look like? We have a new radio access network for 5G. So, the node Bs, the E node Bs, and now we have the G node Bs. This is the next generation node B, and this is actually again, the protocol termination towards the user equipment. Somewhere we have the UE connected to this, and you will see that the G node Bs have connections the user plane and control plane, and they terminate this and they then connect to the user equipment. We will in the future still see E node Bs from LTE, so they have this eUtra user plane, control plane, and the new G node Bs, both. We see the XN interface, the interface that connects the nodes in this new radio access network, and everything that goes to the new next generation or core, that's the NG interface. So everything is now new and next generation. So these are the connection of the nodes to the core. And if you look at the network, you see it's a meshed network. It can be fully meshed, can be partly meshed. So we support many-to-many relations. That's something new compared to the 3G, 2G things that now we support this many-to-many. So it's fully flexible. We learned this already from the radio network also in LTE. With our control plane and we have our user plane gateways. So we have new components in the core. But it's a very simple architecture. Still, we're able to use our old networks, the old LTE networks, and you see that we can still have connections to our LTE core, so that's the evolved packet core. But also the standard tells how to connect to the new core. So you see, okay, the core is also evolving, but you can use both control plane and user plane. Slight differences, but there are ways of coexistence. okay, you don't have to throw away everything, and we'll see LTE for a long time because it's completely sufficient for voice calls, video calls, etc. So what's the status? Since several years we have 5G, at least some test installations, some first devices, so it's a smooth transition. And many people in industry says, okay, that's not a big fundamental difference between 4G and 5G. It's a natural evolution. So yes, everyone invests in 5G, but it's not that big hype, and the normal user will not see that much from 5G. Yes, there are smartphones already available offering some 5G frequencies. If you look here, closer look at the different frequencies today's smartphone support. So GSM band, there we have already 4 different carrier frequencies. Then UMTS, we have 4 more, 5 more, etc. We have in the LTE, we have a dozen more there. We have FDD and TDD, and now, that's new, we also support at least some of the 5G bands, not available everywhere. But this is just the start of 5G. An example, here in Berlin, we have some base stations operating 3.7 gigahertz. So, and they use this massive MIMO beamforming, offering more than 2 gigabit per second for a client. And the round trip time is already at 7 to 9 milliseconds. So we are not at 1 millisecond, but 7 to 9 milliseconds. If you are interested in more of the 5G trials, test beds, and real implementations, follow the link you see here. Okay, so 5G is there, but this was not this big bang, whatever. So it's just smoothly integrated. But the evolution does not stop here. So if you look at what we have right now, our initial 5G networks, they offer a lot, high data rate on the downlink. And quite common, it's a best effort system. You know best effort from the internet. Okay, but to have autonomous cars, for example, we need more and more guaranteed services. Remote controlled robots, whatever. Flying, whatever things in the sky. We need some guaranteed services. So we also have to go towards guarantees. But maybe we also want to send some data on the uplink, so we also want to have more on the uplink. Why? So it's a kind of evolution. Well, there are some ideas of what we can do with the generations following 5G. And one of the ideas shown here, it's called cyber-physical fusion. So we all live in a physical space, and we know that we map and mirror parts of our physical space into cyberspace. So, okay, I don't know if you really want to subscribe, turn humans into information, but at least what we do, well, our health status, everything we see, we can turn into information, what the things do, what happens. So that is a lot of data, different types of data. It is real time. So I touch now a surface. So in the second step, well, we accumulate all the data, and already known since several years are the so-called digital twins. So that's a twin of something that exists in real life, for example, a factory. So we have a digital twin in the cyberspace, and we can do some experiments there, or we can check the health status of the factory there, etc. So we have a replication of the physical space in cyberspace. We have a lot of data, but also maybe low latency, because if I touch something, this can be reflected in cyberspace. Then cyberspace, together with AI, we can forecast the future. What will happen in the near future, max microseconds, milliseconds, on a wireless link. We can look, as we know, discover knowledge, data analysis, etc. And then we see, okay, someone touches a surface. We have to look up immediately, what kind of surface is this? Okay, this is cotton, for example, okay, or this is silk, or this is metal, or whatever, and you touch it, and then you see, okay, I need resources immediately, ultra low latency. If you touch it, the feedback should be within milliseconds. And then you control the actuators. You have the feedback into the physical world. That if you touch this new kind of surface, you will get a kind of immediate, well, almost immediate feedback of the surface. Or if you control aircraft or whatever you might think of. So that is one of the ideas. So this cyber-physical fusion from the physical space into cyberspace and back again into physical space. Wow. This puts some really extreme requirements on our 5G networks. So we learned we have the eMBBs, the MMTCs, the ultra-reliable, low-latency communications. But for some specific scenarios, we have to go further. We need even lower latency, even higher reliability. Maybe we combine different services. So we have to go beyond what we see today with 5G. And that's one part of the next generation. If you like calling it 6G or an evolved 5G or a smooth transition into new, more extreme applications, that doesn't matter. So there's something called IoT 2030, and that's exactly this next step, or tiny steps towards 2030 and beyond. I know people talk about 7G and 8G, but okay. So 6G, we want to have even higher peak data rates. Yeah, maybe terabit per second. Why not? I'd say, okay, more than 100 gigabits per second. Extreme coverage, that's new. Maybe in the sky, near space, over the ocean. Well, complete new coverage area. So gigabits everywhere. Okay? But also we want to have extremely, extremely low energy cost. So it should be affordable devices. Devices that do not need batteries. They do something like energy harvesting, for example. Not only solar panels, but by shaking the device. Well, vibration, etc. We also want to have extreme low latency. Less than 1 millisecond. Okay, but also something like always low latency. So not only end-to-end low latency sometimes, but always low latency. But we know there's the speed of light. This is the limit. So this is not around the globe, no matter what you invent. Extreme high reliability, not only 4 nines, but maybe 5 nines. Whoa, that's very difficult to achieve. So guaranteed quality of service for many use cases. Still, security and privacy, and it should be all resilient, robustness, etc., etc. And then maybe you want to have trillions of devices per square kilometer. So whatever. So millions, billions, whatever. Extreme high precision positioning, things like this. So all the parameters you learned throughout the lectures, you can go even a bit further. Make it even a bit more extreme. Then you end up at 6G. So if we look at the roadmap through the generations, yeah, we start with 1G. We covered here 2G, 3G, 4G. And now, well, 5G, part of it's still speculative, but we see already we go for millimeter waves. We use MIMO, massive MIMO, multi-user MIMO. There's even virtualized MIMO, polarization, different kind of coding technologies. So still a lot of OFDM there. You see the evolved, the new LTE there. What happens then? Well, the definition is for future and further and whatever studies. So we don't know what the future radio access technology exactly looks like. We know there will be some intelligent ways of going, well, exactly at the Shannon border to squeeze out everything that is possible. So there will be some artificial intelligence in the network. So 6G, many people think this is a combination of many new technologies and enhancements of the technologies. So there will be Again, not a big bang and now we have 6G. Unless someone invents something really fundamentally, completely new. On the other hand, we still have Internet of Things. Hey, there's also some new technologies. Since several years, we have a very low data rate technology that offers a nice service. Well, low data rate in the ISM bands, 4333, 868. It's called LoRa. So LoRaWAN, that's a technology that has, well, not extreme high output power, very low duty cycles. And the idea there is to have this kind of very asymmetric situation you find in the Internet of Things. You have large range, up to some kilobit per second, classical star topology. That's the idea. And this LoRa Alliance, you see the pointer here, has already many members, companies, many solutions, etc. And LoRa is, well, an alternative. You can simply set it up. You don't need a network operator. You just buy a device and participate in one of the many networks. We'll give you an example for this. To be honest, there are also some open issues. So, well, it's a proprietary technology by a company, okay. And then if you look into the literature, yes, there are many LoRa devices, but you just heard we want to scale to trillions of devices, to millions per square kilometers. And there are some doubts that LoRa, these types of networks, can really scale. And you will find simulations that say, okay, for smart cities, only some nodes per 1,000 square meters, if you assume 20 byte packets every 16 minutes, etc. And you have no guarantees for quality of service. Still, valuable technology, but you see, the different approaches. You just saw in 6G, we're going to have many massive machine-type communications, millions of devices, and we want to guarantee delay, and we want this and this and this. This is expensive. And here you see a network everyone can set up. Many people like doing this. We also participate. So there are the Things networks. Here you see the pointers, and you can see where you can find those LoRa wide area networks. Many companies use this, for example, to monitor escalators in railway stations or elevators, things like this, to monitor certain devices. I know that beehives are monitored by this. So you see many universities there, also our university, so participating in these networks. So IoT, there are still different networks used. We don't know who will make it in the end. On the left-hand side, you see different networks. We covered some of them, Bluetooth, Zigbee. If you go for higher data rates, we have all this Wi-Fi stuff. If you go for wide area, we saw the 3GPP efforts, 2, 3, 4, 5, 6G. And if you go for low power and wide area, you just saw there's LoRa. There are also some other technologies like Sigfox. There's a narrowband IoT. And now all these new 4, 5, and 6G technologies. I don't know who will make it. It's just here you can also see on the right hand side a map of countries using the LTE standards, narrowband IoT and LTE-M, at least operators offering this to their customers. Many of the operators says, well, you have to use this because it's more reliable compared to LoRa, for example, but then they also want to have money for it. So it's up to you what you can use. Okay, that was basically all about technology, but wait, didn't we miss one thing? Okay, some thoughts about security. This is not a security lecture. Some thoughts about availability. That was not the focus here in the lecture. One thing you have to think of is IoT. We just talked about IoT. IoT with millions of devices. You can read this. We have new attack surfaces. The IoT devices, they don't have integrated security. Quite often we cannot update them. You know how often you update your computer, your mobile phone? Because we have some new features? No, because there are bugs in the software. So what happens for IoT if the devices are compromised and serve as a backdoor for hackers? And this happened already and happens right now to enter clinical IT systems, undiscovered for months. So we have many different systems, weak systems. Well, small operating systems, weak hardware compared to a laptop or a smartphone. We have real interaction with the environment. Think of a medical device. They can have way longer life cycles, something like 30 years in buildings. And no one knows how to patch the Internet of Things, how to update, who's responsible 10 years from now for a device that's integrated in a building. And how do you integrate today security features needed in 30 years? That's almost impossible. So that's really open topics for the Internet of Things. Not that easy to answer. But also, without the things, even for stronger devices, we all know that even without an attack, software bugs do happen. Yes, we know this, even using the best software engineering principles. So sometimes we simply interconnect networks, also wireless networks, for new features, and then we have unforeseeable interdependencies. Plus, we have short innovation cycles, so we don't have much time for testing. Additionally, there are not that many vendors of hardware. You may think of, there are so many different mobile phones. Yes and no. If you look inside the phone, for example, the modem technology, there are not that many companies actually manufacturing this, the chips for it. So if you have a simple bug, it may affect thousands or millions of these networked systems. What is the result? So it's very simple to affect millions of users. Many years ago, there was a software update at one of the German network operators banning millions of users from the network. Quite often, we have misconfigurations at internet routers and they cut off autonomous systems. Now think of the mobile phone network. Think of your smartphone. Well, what happens if you want to call the ambulance? What about high availability? What about redundancy? Usually today you use your smartphone for everything. What if there's a software bug? Emergency calls? What if there's a software bug in the network? We saw with 6G, the requirements. We saw software-defined networks. We saw virtualization of everything. What happens if there's a bug? Suddenly nothing works anymore, and there are not that many people knowing how to pull which ropes in this case. So just to think about. Okay, also here at least some questions. Is 5G all about higher data rates? What else do applications in the future need? What are the 3 main application domains of 5G if you look at the standard? Why do we need more than 5G? What could be applications? So think of, be creative. Go ahead, check for LoRaWAN at your place. Maybe there's one. You can participate. What else could be used for Internet of Things? What are the pros and the cons for the different networks? And although this is not a security lecture, we have several lectures for this. Think of vulnerabilities of mobile and wireless systems. Think of the many systems depending on these networks. Think of yourself depending on this. And think what happens in case of a blackout. Okay, so thanks a lot participating in this lecture. Take care. Have a lot of fun with mobile communications.